So as I said, today's topic is about key selection. How do we choose keys for our tables, and what the impact that it has on our application going forward, on the way our queries are running, on the way our integrity is going to be maintained over time, et cetera, et cetera. Now, when I upload the materials and the demo code for today's sessions, you're going to see that there's plenty of stuff that I'm just skipping because this was originally designed for an hour and a half, and we have only 45 minutes. So again, pardon me. I think you're going to get the complete picture even without the little demos. Just be aware that there's more material when you download it. So my first question, and you can ask yourself that question if you want to write it down. Does anybody volunteer to tell me what is a primary key? Yes?
Primary key is a unique identifier that basically gives a database row its unique that allows it to be retrieved, that allows it to have its own unique identifier.
It's a unique identifier. Okay. What type of identifier?
Other than being unique?
Yes. Okay, 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 okay. Any other thoughts? What is a primary key? Okay. By the way, when I do interviews for data people, that's usually the first question that I ask in an interview. And you would have passed. I'll see you in a minute. Yeah, but most of the time I get much different results. Anyway. So there are several types of keys. We can actually define many more. For today's purpose, we're going to focus on these type of keys. So a simple key is a key that consists of a single attribute or a single data domain, or the SQL implementation, a column in a table, right? So a simple key will be a key that consists of a single column. A composite key will be a key that consists of more than one data domain, more than one column. Anyone know what a candidate key is? Okay, so a candidate key is any simple or composite key that uniquely identifies the relation and can be used to uniquely identify it, right? So if I have a table that has countries, so I have the country name, I can use that to identify the country. That's unique, right? I got the country internet extension, the dialing code, the longitude, latitude. There's pretty much everything about a country that will make it unique. So in a countries table, I'm going to have potentially many candidate keys, many such attributes, many such columns that can uniquely identify the relation, or, as you say, the row in the table, right? Okay. So what's a primary key? What's the difference between a primary key and a candidate key? A primary key is a key that was chosen by the database designer among all candidate keys to represent the relation in front of all the other relations in the database. So in the sense of my countries table, for example, if I choose the country ISO code or the country dialing code as my primary key, from that point on, that is going to represent the country in customers, in orders, and all the other places where I need to identify country, correct? So that is the proper definition of a primary key. So it is a unique identifier, but it's pretty much random. So you can choose any of the candidate keys, and we'll soon see what the impact of that will be. Okay, artificial or surrogate key is a key that does not exist in the real world. It is not part of our relation, and we add it to the table for whatever reason to serve as a unique identifier. That can be a GUID, right? A GUID doesn't tell me anything about the country, right? It's completely artificial. It doesn't have any information about the country. Same for a sequence, identity, any one of those enumerators or random strings or whatever you use, that's going to be an artificial or a surrogate key. And a surrogate key, by definition, is to replace and existing one of the candidate keys. An intelligent key, on the other side, is a key that tells us something about the relation. So a country name, a country dialing code, a country internet extension, these are all intelligent keys. They give us information. They are part of the relation. They're not something that we add on top of it. And the last type is a natural key, which is a special case of an intelligent key that we like to think of it as something that is inherent and inseparable from the entity that it represents. An example. So let's say we want to represent a person. This is always one of the trickiest things to do. How do we tell people apart? So if I can use, if it's only people in the US, let's say I can use social security number, SSN, that will work. So that will be an intelligent key, but that will not be a natural key. Why? Because if I find a dead body naked in the desert, and I want to identify that person, an SSN is not going to help me, right? It's not part of the entity. What is a part of the entity in the case of a person that can help us identify it? DNA sequence, dental, retinal scan, many others. By the way, fingerprints cannot identify people because identical twins have identical fingerprints too. This is something that I learned when I once gave this session, and I gave the example of fingerprints, and after the talk, somebody came to me, and he was all riled up and says, "You don't know what you're talking about." I said, "Okay, well, no, fingerprints cannot be used to identify people." And I went and checked it, and he was right. So anyway, a little bit of information. So the debate today, and I'm going to use the example of whether to use a surrogate or a natural key, is a long, long, long debate that goes back to the forefathers of the relational model. So today, unfortunately, in most cases, when you see a table, there's always a table name ID, right? And that's either a GUID or an identity or a sequence or some sort of artificial key, some sort of surrogate key. And the original model that Dr. Codd designed, and this is Dr. Codd on the left. He's the original founder and thinker and forefather of the relational model. And on the right, who knows who is it on the right? That's Chris Date. Everybody heard the name Chris Date? Yeah, so Chris Date, he was kind of the successor after Dr. Codd kind of grew old and didn't really want to deal with that anymore. But even they had kind of different opinions about the use of surrogate keys. And so this debate goes really, really long by. So the source of the ID concept in people's mind actually has a historical reason. So when we had punched cards and magnetic tapes, they all had physical address pointers. The cards had a sequence to them. You had to put them in sequence. If you had the, I don't know about you, but I still programmed when I was a kid with punched cards. And if you drop them on the floor and they get out of order, yeah, it's a hassle. You're laughing. You've probably experienced that, right? Magnetic tapes, same thing. They had physical sectors, and whenever you wanted to access a specific data point, you always used the pointer, the physical address in the tape. And that concept lingered on. So memory addresses, but even with spinning hard disk came, and we could have pretty much random access with spinning hard disk, not to mention SSDs. People still had the sequential mindset that said everything must have a pointer, everything must have a handle, everything, that's the only way I can access pieces of data, but that is not the case with a relational model. Because it's a logical model, it's not a physical model, it has nothing to do with pointers, it has nothing to do with physical addresses. Actually, in RDBMS, one of the desired properties of a relational database is to be completely physically independent. So the logical model and the physical model ideally would be completely separate. Unfortunately, they're not. That's the PDI, physical data independence. Okay, so there are two camps in the world. One, which consists of 99.5% of the people, and this is what you'll see in most textbooks examples, this is what you'll see in articles, and They all form, I call them the pro-artificial. Those are the camp that preach for always using surrogate key. Whatever table you have, always put an ID on it, use that as your primary key. And they have claims. So I did research, and I tried to come up with the most common claims. I also, you can imagine, in my 20 years, I had several debates on the topic. So, I absorbed claims that I heard from all camps. And I'm trying to summarize it here before we go into the demo, because I really want to spend most of the time today on the demo. So the first claim that I hear is that in some cases, there is no natural key, and artificial key is the only option. Now, that's a problematic statement, because what you're saying when you're saying that there is no natural key, or there is no natural key in my table or relation, that means I cannot tell the rows apart. Regardless of the database, those rows represent something in the real world. Those could be orders, those could be customers, those could be countries, but it's always a model, right? It represents something in the real world. And if I can't tell my rows apart from one another, there's no candidate key, that also means that in the business term, I can't tell those entities apart in the real world. So I see one person, and I can't tell which one of the John Kane it is in my database because I chose name as the primary key, right? Something like that. And by the way, if I choose person ID and give them sequential numbers, that's still not going to solve my problem, because I still have John Kane, two of them. One is number 1, one is number 150, but I still can't tell them apart. So if one of them walks into my store and tells, I'm John Kane, which one am I going to associate it with? With the one that has ID 1 or with the one that has ID 150? If I have no logical way to tell them apart, my sequential identifier is not going to help. This is interesting that, do you know who this guy is? This is Aristotle, and Aristotle formulated the law of identity that says to be is to be something in particular, which means if there's nothing that tells you apart from anything else, you don't exist. But that's a philosophical. Okay. Another claim that I hear often is that natural keys can change and artificial keys never change. By the way, that's 100% correct. So if I choose a country name as its primary key and the country decides to change its name, I'm going to have to go and change everything in my database. If I use ISBN for my book and the ISBN changes, I'm going to have to go to my database and make it work, right? While if I use IDs, the IDs will never change. Does that make sense? So I don't have to do any extra work in case something happens. So my first question is, how often does it change? And that really depends on the key that you choose. Because if I choose a country name, how often does a country name change? Not often. ISBN for book. Anybody know how often ISBN changed? I think in the last 100 or something years, it changed 3 times. Every time they ran out of digit, and they had to make the ISBN number longer. So it did change, but it changed once every 30 years, right? So unless you choose a key which is highly volatile, that's not really a challenge. However, that also tells you that one of the desired attributes of your keys is that they should be stable, right? Or relatively stable, because you usually don't want to deal with it. But when you want to deal with it, there's a mechanism in every relational database, every major relational database, that's called cascading referential constraints. So when I define a foreign key, I can always add the clause that says what to do in case of an update. So on delete, no action. On update, cascade, which means when I update the parent, I want all the children to be updated as well. So I change the country name in one place, and it will go change it in all the tables in the database. And that was the mechanism that was exactly designed to deal with that. And the last thing is that artificial keys can change, and they usually change when it hurts most. I'm sure, has anybody here tried to merge 2 databases from 2 separate systems into a single database, and they both have IDs as primary keys? Yeah. Okay. So this is where it hurts most, because now you have to be able to tell that this John Kane is this John Kane, but you have no way to tell it. because they use some random ID, and that ID can be anything in any database, right? It doesn't mean anything. Okay. Another claim that I hear is that natural keys may be long and complex, and that is true. We'll see that in a minute. So with each level in the hierarchy, they become longer. What do I mean? Let's say I'm keeping a tab. I have a database that keeps tab of bank accounts. And I want to use natural keys. So for the banks table, I will have bank as the bank name as my primary key. For the branch table, I will have the bank name and the branch name. And then for the account table, it'll be the bank name, the branch name, and the account number. So now, the more levels we have in the hierarchy, our keys tend to become longer and longer and longer, and they become complex. In SQL Server, there's a hard limit of 900 bytes per index key, which kind of limits your options, but in other engines, that might be different. I don't want to deal with multi-column joins now. We'll deal with that later. Okay. But this is my favorite claim. This is the one that I like hearing the best. So artificial keys help improve performance. I'm sure you've heard that before. And there's nothing that turns me on than a meaningless overgeneralized sentence like this. This doesn't mean anything. So then I ask you, OK, how does it improve performance? And some say, OK, because you're always joining on a single column, your predicates are always single predicates, therefore your join conditions are simpler. It's much easier to write a join where country ID equals country ID versus country name equals and something equals and something equals, and I have to write these long predicates. So, right, this is simple to write. There's, in SQL Server, there's how many people here work with SQL Server? How many Oracle? Okay. So most of you are SQL. I'm not sure if you're familiar with the ever-increasing clustering effect. So whenever you have a column that is always increasing in value, that means that the last page of the table is always going to be in cache, mostly going to be in cache because it's frequently used. However, that's not necessarily a good thing, and we'll see that in a minute. Another claim I hear is that artificial are usually shorter, which means a smaller database, which means faster response time. We'll debunk that in a minute. What else? I don't want to deal with fragmentation right now, so let's skip that and move on to the natural. So about 0.5% of database designers, and your humble servant upon them, actually do believe that there is a valid case in probably most tables to at least look for the natural key. The first thing is that natural keys have business meaning. That means that if I choose a country's name as the primary key, when users want the database to produce reports, they're not going to care that Australia has the number 5 in my database. What they will ask, they will want to see all orders from Australia in the year 2014. I'll never get a request for a report, show me all orders from country number 5 in 2015, right? Because in one database it could be 5, in another database it will be 7, in another database it will be 260. So the natural keys already include the information in them, so I'm not adding anything to my database which I don't really use. So artificial keys are never queried for directly. I will query them in joins, I will query them whenever I need to do referential, but I will never query them directly. We'll see the implication of that. Queries on tables using natural keys require fewer joins. And this is probably the biggest impact here. Because if most of my reports want to see country name, and I use that as a key, I just saved the join to countries from every query in the system. Now do that for, and we'll see how that happens. We'll do that for 3, 4, 5 tables, do that for 80% of the tables in your database, and all of a sudden, 80% of the joins in your code, gone. Now, what will that do to your query performance? We'll see that in a minute. And the more familiar and meaningful the key, and this is now the second trait, desired trait of a key that we discussed. The first one was stable. This one will be familiar and meaningful. Because if this is what the users want to see, that's my best candidate for a key, because that piece of data is going to be in all the relevant tables. Bypass joins I'll show you with a code. OK. Another thing, data consistency is maintained explicitly when using natural keys. So ideally, for every table, you should always research each and every candidate key and at least put a unique constraint on it to keep your data consistency, right? Otherwise, you're going to get duplicates, and then that's a slippery slope from there. So when I use IDs, if I use ID as primary key and I don't have any other unique constraints, what's preventing me from inserting the USA 5 times into the table? Nothing. Each one's going to get a different ID. They're still the same USA, right? But now I have to do extra work to keep this consistency. While if I was using natural keys, that would happen on its own. So artificial keys enable logical duplicates. Again, I don't want to deal with the clustering, but this is more of a performance. I want to move on. OK. Artificial keys are the de facto standard, and that's what I mentioned at the beginning. If you open any textbook, if you look at any article on the internet, almost every table has table name ID as the key. And because people learn from these textbooks and you read the internet and these are the articles that you see, you assume that that's the only way to do it. And today, I hope to rock your world a little bit in that regard. So even things like ORMs, I had a personal experience with LinkQ for SQL Server that didn't cache composite key rows, and many, many others. Yeah. Data, statistics, and optimization, I'm going to show you in code. Modularity and portability, this is something that I already mentioned. If you have 2 databases that use natural keys, joining them together is as easy as writing the insert select scripts. That's it. Right? All the entities are identifiable. You can immediately tell which one is which just by looking at the key. Which means migration to other platforms is going to be easier merging with other databases. But hopefully, maybe one thing that we'll see, and this is not a technical thing, but it took me a while when I started learning SQL and I saw, I also designed my databases, everything, IDs, integers, GUIDs, no matter. And I started reading more and more, and there was one day when this thing just clicked. And I started looking differently at the relational model using my keys, and it just became this beautiful thing when you look at it, and you can see immediately what the business is about and what goes on in the data. And I hope to prove it in our demo. So we're going to build 2 very small databases which hold a database of websites. For each website, we're going to have a URL. And we're going to keep the country and city of the owner. Our data consistency is crucial, so let's jump right in. Now, this is one of the places where I am going to skip a few things, but we'll start with the one that will look more familiar. So I'm not going to go through everything on the script. I'm just going to focus on the tables. So I have my countries table, country ID, integer primary key, ISA code unique, country unique. I did take care to enforce all the candidate keys. And now I have a geodatabase that has country codes in one table. I'm just populating all of them. They're getting generated with IDs. Same for cities, city ID, and city. And then there is this many-to-many table where I'm using the city names as if it was its own entity. So I have a country city ID, which identifies the relationship between a specific country and a specific city. So far, OK? Right? OK. Now, the first thing that you want to notice is because I took the original data and now inserted it to tables with IDs, and I need to use these IDs for the joins, and I don't know what they are, What I have to do is go back to my original data and do the join all over again just to figure out which were the IDs. Otherwise, I wouldn't be able to do it. But the end result, and this is the main table that we're going to work with, that's the website, which tells me which is the website, which is the URL, the country-city combination for the owner, and some sort of filler just so the table isn't really small. The natural keys, this is exactly the same schema. The only difference is the key selection. So here, look at this very odd thing. The country, which is a varchar 50, is my primary key. Okay, that's going to be Australia, USA, England, whatever. So now, when I go, so far the insert statement is the same. My cities table is going to have a single column. By the way, this is the second highest level of, this is the highest level of normalization. This is fifth normal form. A table that is all key is fifth normal form. Okay, that's like way up there. And now, for my countries, cities, note that because I don't have the IDs, I use the actual names of the countries and cities, the insert only has to do a single join between my source table and my country based on the country name. No need to figure out which IDs. You'll see more of it soon. And the last thing is my websites table. And here I chose the URL as my primary key, country, city, and filler, similar to the other one. So if you want to look at this is the artificial one. This is the schema for it, which we just described. And this is the schema for the natural key one. No IDs whatsoever. Only use the actual attributes. So far, so good? Questions? Okay. Okay. So when you're going to download this code, I'm not going to run through it because we're short of time. There's a full check of the claim, whether or not it's bigger to use natural keys or artificial keys, so you can see the actual database sizes. There's a little benchmark that checks insert performance into those two databases using a pretty neat trick. You can read it later. I don't want to go over it right now. I'll save you the time. I can tell you that the insert performance to a database with sequential IDs and natural keys is pretty much the same. Right? There was 1 second difference between the two. One was 40 seconds, the other one was 41 seconds. But what I really, really want to get into is the queries, because this is where all the fun is. So we're going to start with the first query pattern, which is called a singleton lookup. A singleton lookup means that I have predicate, an equality predicate, and the predicate is on the key, which means this is guaranteed to return 1 row, right? Okay. So far they look pretty much the same. Select star, artificial keys is the name of the database, natural keys is the name of this database. Let's see what happens when we run both. By the way, you see that the predicate is not going to return anything, but what I'm really interested in is the execution plan. So the top one is the artificial keys, and the bottom one is the natural keys. And because my question was on the URL, I asked where URL equals something. When I used the website ID as my primary key in SQL Server by default, that also means it's the clustered index. That's a different topic for a different talk, whether or not it's a smart choice. But anyway, the non-unique index, the unique index, which is now on website, doesn't have all the columns, and therefore it requires a key lookup. While as when my clustered index primary key is on the URL itself, then my question is immediately retrievable from the index, because that's what my table is sorted with, right? So even though for this you're not going to see much of a difference, and by the way, don't trust those 67 versus 33. In this case, I can tell you, for a singleton lookup, no difference. It's a few additional IOs, no big deal. However, things start to get trickier when we look for ranges. Yes?
Did you have on the artificial, did you have the ID included in the index?
The ID is always included because for physical implementation reason, at least with SQL Server. I don't want to speak about other engines that might have different implementations. So the next query is very similar, but instead of having an equality predicate, now we have a like predicate that is going to return a range of rows. So in my case, every one of these random strings that starts with an A is going to get returned. Now, let's run these two queries and try to understand what's happening under the cover. And what I want you to notice is that for the artificial keys, it actually scanned the entire table. And for the natural keys, it did the exact same plan as before. Because if my rows are ordered based on URL and I'm looking for a range, all I have to do is find the start of the range and then follow the rows one by one by one by one by one until I get to the end and I got the answer. I got everything. That's why a single clustered index seek is enough. However, because for the previous one, I had to do a lookup for each row to get all the other columns other than the URL, now the optimizer decided that those lookups are going to be so expensive that he might as well scan the whole table. Now, this is a big difference in performance. And the queries, even though they seem innocent enough, right, as far as we're concerned. But if you're aware of it, this can be dealt with by careful tweaking of the indexes, but it just happens on its own when you use your natural key. However, let's start to look for some more challenging queries. So, for example, I want to see the top 10 countries with the largest number of websites. Of course, I want to report the country name, right? I don't want to report its ID. Therefore, I'm enforcing a join to countries. So here is countries on country ID equal country ID. And I need the top 10 from country, and I need the count from the websites. So I have to group by count, group by country, order by count, retrieve the count, and retrieve the top 10 countries. I have to go through websites to country cities to find the link between the country and the city, and only then to go to countries to get the country name. Does this seem reasonable? Simple enough query, right? This is what you're used to doing? OK. Now, the same query with natural keys. And this is where SQL becomes plain English. So I look at this query, and this tells me exactly, without having to know anything about the schema, what the query is returning. So go to the website, group by country, order by count, and give me the top 10 by count. We just eliminated 3 redundant joins. You want to check performance of these two guys? This is the plan. It was so expensive that the optimizer opted for a parallel plan versus the bottom one, which, again, scanned the whole table. Both of them did, because there's no filter, but never mind. But here, you can see that the scan immediately to the count aggregate, the sort, without having to go through hoops to figure out all the various joins first. Now here, the percentages are lying in the other way. So this is not 70-30. This one is more 99 versus 1 in terms of performance. OK. Another cool thing that you can do, so even with natural keys, you occasionally need the joins. So if the report requires one of the columns that is not part of the key, we're going to have to join back, right? There's no way around it. However, there is a big difference even when you have to join, because we don't have to traverse the entire hierarchy. Watch that. All I want to show is the ISO code for all countries that have websites. I'm just looking for existence, nothing more. To get that from the artificial guy, I have to go to the website, but the ISO code is in the countries, so again, I have to go through country cities. Again, I want to remind you of this. This is my website. To get to countries, I have to go through country cities because the ID is here. And this is just the country city ID. This is this ID. And to get this ID, I have to join both tables. There's no way around it. So, to do that, with the natural keys, look what I just did. I just joined websites directly to countries, even though there's no foreign key between them. They're not related. They go through the country cities. However, if we go to the schema here of the natural keys, the country that is used here is the country name. It's the same one that is used here and the same one that is used here. So there's no need for me to go from here to here to here. I can go from here, from here to here directly. And this way, sometimes we have 6, 7, 8 levels of tables just to figure out the IDs to get back to the root table that I'm looking for. And here, you can just shortcut the whole thing. And even when you need a join, you need 1 and not 20. How are we doing on time? OK, we're good. Yeah, I can show you the performance for this, but you're going to trust me that it's, not. Do I want to get into that? No. So this is something that you're going to, when you browse the code, when you download it, there's a couple of more examples, interesting examples here. I do want to show what happens when we do an update. And this is where you're going to pay the price, right? So if you remember, or you don't, when I wrote, you can see for all my foreign keys, I used cascading referential constraints. So I say whenever there's an update, I want you to cascade the update. So when the parent changes, go and change all the children. But if the parent is deleted, I want no action, meaning stop. You cannot delete a parent, you're going to leave orphans, right? I cannot delete an order without first deleting the order items, right? So this is the default action. On no action is the default, but I can specify cascade. With the ANSI syntax, you can also specify set default or set null. But this is not implemented in many engines, but anyway, never mind. So let's go back here. So with my artificial database, changing a country name is very trivial. Update countries, set country equals Ivory Coast, where the country was equal Côte d'Ivoire. They did actually change their name, Ivory Coast. So that's not going to take a lot of I/O. You can see it took only two logical reads, and that's pretty much it. That was pretty fast, right? However, if that happens with my natural keys database, because the country now appears in all of the various tables, when I update this guy, it's going to have to go and cascade the updates to all the other tables. So this is going to cost us more. And as you can see, there were plenty of tables that needed to be updated, even created work file tables, internal tables to maintain consistency. So this was more expensive. However, what I want you to consider is that although this is true, this is going to be more expensive, how often does a country name change versus how often you write queries like before that want to look at the top 10 websites or the top 10 countries or do all sorts of analysis about our database. Questions? Okay. So what I want you to take away from the session today is two things. Whenever you're faced with the challenge of designing a new table, the first thing you need to ask yourself, is there a natural key that I can use? And there should be more than one. If you look and you find and you say, hey, there's no key that I can use, your table is wrong. There's something wrong with your design. Are there a few natural candidates? In many cases, there will be. In that case, you start asking yourself, okay, which one is the simplest and most familiar? Meaning it has the most chances of appearing in queries, in reports. And that's, if you use that one, you're going to eliminate the most number of joins. How stable is it? How often does it change? Remember, there will be extra work to be done if the value changes. Again, choosing a stable key that doesn't change often, it's not going to be an issue, right? If we need to change a country name and it has to update 10 billion rows, no problem. We'll do it over the weekend, let the transaction finish, and be back afterwards. How will it be used logically? How will it be used in query? This now more relates to index design and more physical design. What will be the physical access patterns? What will be the common query types for this table? And hopefully, this will give you enough information to evaluate. And I'm not saying always choose a natural key. But if you walk out of here and the next time when you're faced with this, you're at least going to look at the option of using a natural key, then my work is done. I got quite a few resources if you want to read about relational database design and keys and all that thing. I highly recommend Joe Selko's books, especially this one, Data and Databases, Concepts in Practice. I learned a lot from Joe Selko. He's also one of the few advocators of using natural keys. And yeah, that's about it. So if you have any questions, we still have like 2 minutes. No questions. Very good. That's all, folks. Thank you very much.